So why material science? Because the CEMEF, it's a material forming research center, and we deal on any kind of materials, polymers and metals. But we also deal on numerical simulation and also experimental observation. Yesterday it was not necessary to do that. So the idea is to improve our knowledge of the material behavior from the beginning of the material. So when it was born, all the chain of the life of the material, so from the solidification, for example, casting to forming, but also including heat treatment, joining, welding, until the end of the material and the final properties also on the final part. So the idea is to use finite element simulation in order to help us to understand at different scale who is the life of the material. So we implement this. You cut the film, yes. we implement this in order to see. Okay, and I start again.
You want to restart the computer?
So the idea is to develop a numerical simulation in order to understand deeply how the material, the evolution of material at different scale. So one idea is to use a classical level set approach in order to define the position of different material at a different scale. It's okay? Thank you. So you understand that I am talking about material. So I continue. So the idea is to take the advantage of these techniques about a level set interface in order to track all the moving boundary of different materials in terms of, for example, coupling fluid and solid during heat treatment. The other idea is also to use this moving boundary in order to study the evolution of microstructure during thermomechanical operation. Thank you. Thank you. So I try to follow this outline. So first, briefly, I present this numerical framework in order to understand what are really our goals. Then I try to have time to present the application to grain growth simulation. It's very important for the material science to know the evolution of the microstructure of the material. Then the application of this to the knowing of the evolution of damage from the beginning of the material, but also the evolution of the damage after forming and in the final part, because this is very difficult to predict, and this is very important for the industrial use of the part. And after I finished, if I will have time, to the application to heat transfer and concluding remarks. So our job is driven by industrial needs. So our core business is material forming. So we try to work at different scale, because this is the good answer for the industrial people. So from the, of course, microscale, but here today is from the mesoscale to macroscales, and for example, here you have a forged part in which we have the grain distribution. This grain distribution is very heterogeneous depending on the process, and this is a very large difficulties for the final part. But we have also sometimes the evolution of void, and this evolution of void could also leads to some damage, and this is also very important to be able to predict this. And of course, macroscale is all the process around heat treatment, including heating, but also quenching. And this is also very important to predict the final properties of our part. And this is just for fun, in fact. So here for the material forming, we need to understand all the physical equations that who drive the evolution of material, and also bridge the different scale for mesoscale to macroscale. Of course, we are talking about forming, so it's large strain, large plastic strain, so it's very important also to use this and to have a different geometry. And of course, process optimization, this is required strongly by our industrial partners. So we have also to deal with different geometry, because sometimes the geometry are very complex. So we take benefit of a large of publication and state-of-the-art in our community from different famous paper and scientists here. And especially this, the 3 items, immersed boundary, embedded methods, and monolithic approach. So for us, it's a very large help of our presentation. So our numerical tool is based on level set representation with mesh adaptation and the multiscale. So few words about the level set techniques. The idea is to immerse, for example, a solid into a fluid, and to compute the distance between the solids to the surrounding material, for example, the fluid. So we build this distance as a function, and we signed it as a level set function. It means that this function is positive inside the solid, for example, is negative outside, and null at the interface. So this is very useful. After that, we create a mesh with in order to follow the interface with the gradient of this level set, and we have only one mesh. This is very important. We just refine the surrounding of each object on this mesh. Of course, these different objects have different behavior depending on the material, for example, solid, fluid, and so on, and we have to use a mixed rule for the material properties. This is the basic idea. For geometric representation, this is very easy, because this level set can help us to have, of course, very easy representation of square, sphere, and so on, but also more complicated representation, computed the distance between complex surface. Also with some cell, a random cell, like, for example, for powder, metallic powder, or for porous material. But also, if we have the description, analytical description of the interface, we can also use this analytical description in order to create the level set. So the main advantage is the separation of the different phases for this. So for us, it could be very interesting. So fluid, solid, different fluids. Flexibility in terms of moving, adding and moving different objects, because, for example, when we have woven like with this dimension, we can put a large part, and we can remove the part, added another, and etc., without necessary to remesh and to have a few days to remesh the part. So this is very powerful. And we have also to have the gradient at the interface in order to have the mesh adaptation. So for the meshing, so here we have the very simple scheme here, in which we have the inclusion with isotropic mesh, and here the matrix, but we have also a thickness of an interface here, in which we have to be very precise in terms of geometric description. So in this case, we use a priori adaptation. It's interface description with the metric based only on the geometry and the zero value of the level set function. But we need also to improve the mesh in terms of mechanical computation. It's term of error estimator in terms of stress, strain, and so on. So in this case, we compute also an a posteriori error estimator, MN. So in fact, we combine the two estimators in order to create this mesh with a gradient at the interface here. So here is the inclusion, and here it is the matrix, and here the interface. So now we have to solve the convection equation. It's the moving of this level set interface following this very classical equation. So if we focus on the v function here, this velocity is solved by using classical Navier-Stokes equation. We have a lot of papers on this subject. So here, just an example. Here we have the filling of a box, transparency box. Here is the experimental observation, and here we make the simulation of this approach in order to compare the two ones. So there is still some difference, but it could be interesting to see that the flow of the liquid is correctly represented by this. But today, this is very important to say that we work also on the signification, the meaning of the velocity in terms of evolution of grain boundary. So it means that here it's a classical map of a grain here, and this grain can move depending on the operating condition, for example, depending on heat treatment or pressure and so on. So it's important in order to have the final metallurgy distribution to follow the evolution of each grain here. So we use this velocity in order to follow this. So this velocity is based on the metallurgical and physical approaches. So all the parameters normally are well known by the specialist. So we introduce this velocity with these terms. So M is the boundary mobility. And here we have the boundary energy. Here is the term of curvature. Here the store energy, and here is the normal at the level set. So in this approach, we can also take into account some new particle inside the grain. We see more at the end. But with this distribution, we can have this respect to the grain side evolution. This is very important. To respect the second phase fraction and morphology, this is also very important for some material, taking into account the capillarity effect, the store energy, and also Zener Pinning is quite strange word. I'll explain you later what is the Zener Pinning in microstructure evolution. So for this grain boundary motion rate equation, we solved it. So here we have the mobility. The mobility is in terms of a classical equation with T the temperature, Q is the activation energy, and R the gas constant. So here this term is the driving force per surface unit. So it is the equation who permits to the grain to growth or to have to avoid some obstacle and so on. So this term is the dislocation, so the energy, linear dislocation energy. Here is the dislocation density, and here is the grain boundary energy, here the grain boundary curvature. Just here an example, so we have the evolution of mesh. So all this 2D example are meshed. Just here we have the description of the interface with the gradient of the level set, and we can see that there is the grain, some grains are growing and some other are disappeared, just based on this evolution here. So this formulation is used for the recrystalization formulation, so I don't have time to go in detail about that. So it's a very classical convection equation in which we describe precisely the velocity of the interface. It means that the boundary of the grain. And we have to solve this equation here. So here some very important feature of this approach. This is very important to focus that we need absolutely to have an automatic remeshing during the operation because the forming induces a large strain, so we need to remesh every time in order to follow the evolution of the material. So we have to solve this equation here. So this is an example of this result. So here is the representative volume. And here you have the grain, and we try to see the evolution of this grain during time, for example, during the heat treatment. Heat treatment is a good candidate in order to see the evolution on grain. So you can see that this evolution of grain, so here a cut in order to see some grain are occupied all the space. Some are disappeared, some blue are disappeared. So it's just due to the equation we solved and the physical parameter we put on it. Zener pinning. So this is very important problem because this is the real and strategic problem for superalloys in aeronautics. The Zener pinning is due to the small rigid particles we have in a superalloy coming from the history of casting and so on. But this particle can block the evolution of the grain during the processes. And also we have to take it into account, so here the level set interface here an example of a scheme of this particle, and we have to solve the evolution of the interface during the moving of the boundary and the obstacle of this particle. So the name is the Zenner Pinning. It's a very important point to solve for the industrial user. So here just a scheme of what we solve. So we solve this equation with two grain. Here is the second phase particle and here the level set. And we try to solve this and to see the influence on the grain boundary. And this is very interesting because the influence could be nefast to the metallurgy. So here it's a real microscope image in which we have a small particle of second phase, and we passed a mesh on this image, and we create this finite element mesh in which we apply the boundary condition, for example, thermomechanical, and we try to see if we have some problems. So the very small particles are here. It's less than 0.5 nanometers, and here is around 1 to 10 micrometers, so it's very small. So if the particles are inside the grain, no problem, the grain can move following the classical stored energy. But if the particles are close to the interface, there is a specific problem with a very large grain together a very small grain, and this is a big problem for the industrial partners. So this is an example with a nice distribution of grain size, and during the heat treatment, we can have that there is heterogeneous size of the grain, and this blue grain, this is a big problem for the end user. Okay, so just here an example of this Zener pinning. So here you have this particle, and we have here the grain of the metal here who move. And here it's interesting to see that the evolution of the interface here cross some particles following the equation I showed you before. So this is a crucial point for some complicated material. So the second part is the application of this microscale studies on the knowing and the knowledge of the evolution of damage. So the damage can be coming from the initial casting. For example, we can have some void on the initial part, and progressively, due to forming, we can have the evolution of this void until rupture. But we can also have the closure of this void. This is also could be interesting to be able to simulate this. So in this one, it's very important to have also, as the previous one, to have the image coming from, example, the tomography or microscope in order to have the image of the initial defect. We passed a mesh on this, and after we apply thermomechanical condition on this mesh in order to see the evolution of this damage during the process. Like here is a rolling process, it's a bar who passed through a cylinder in order to have a longer part. The idea is also to be able to produce a macroscopic law in order to have an input to the macroscopic simulation. So particles and void representation. So here we apply the level set in here 3 domains. We have the matrix, we have the inclusion of inside the matrix, but we can also have the void of the matrix, and we define in this 3 domain and 3 level set function. Concerning the mesh around this inclusion, in fact, we can apply the very simple geometrical matrix here in which we refine the interface in order to capture well the geometry. But we can also apply coupling to the a posteriori error estimator based on the mechanical value like stress, strain, and so on. So here an example of the matrix, the void, and the inclusion. So for the mechanical properties, in fact, each domain has its own properties. For example, matrix could be elastoplastic, inclusion could be rigid plastic, incompressible. But for the void, the incompressibility is completely out of scope because we can have 10 times the size for the void, so it's not incompressibility. So we have to add another behavior. So perhaps we have 3 behaviors, and we have to mix the properties at the interface here. So some elements are crossed by the interface, so we use a very simple mixture law in order to combine the 2. This is a very simple approach, but if there is a very difference about the properties of the different objects, it could be difficult to apply this. And in this case, we try to minimize, in fact, the dimension of this zone, and we have to change and to evolve the mesh in order to decrease the thickness of the interface to have a very, very small thickness here. It's like a very body-fitting mesh adaptation. This is also a possibility. Okay, so here we have an example of this mesh, so a single mesh with just refining around different zones. So here refining around a zone in which we need a geometrical adaptation, and refining here because we know that in this zone there is, for example, localization of stress or strain, and it is very important to have a refined mesh here. So how to deal with the nucleation? So we have an inclusion and we have the matrix. So there are two choices. We can have during the processes, for example, heat treatment or a tensile test, for example. We can have a debonding of the inclusion from the matrix. So we create a void. And after we propagate this void during the simulation. The other possibilities is to have a fracture of the particles and to have different particles from only one. So all these criterion are based on the stress state. Here is the normal stress here with a critical one, and here is the stress perpendicular to the principal stress here. Okay, so this is very important to see that, for example, here in this zoom we have one inclusion. So we make, for example, this tensile test. We have one inclusion with a fracture here. And here it's the different inclusion here in this direction. And we make a tensile test in this direction. And we propagate the void here due to the fracture of the inclusion here. So you can see that, so it's difficult, but the void is meshed, that we mesh this zone too. Okay? So now it's important also to rely this with the experimental one and to know the evolution of this following the real microstructure. So we take benefit of real microscope images in order to create the mesh. And after we applied different operating conditions on this mesh. So in this case, we have first the tension of the sample and then shear tension. And in this one, we have first shear tension and after the tensile test. So this is important to know how this damage follow the operating condition in the real life. So we can see that, I'm not sure it's visible, that this strain path is worse than this one because we have more localization on plastic strain in this zone than in this one. So here we have the same approach in 3D, and here we have an initial inclusion in a matrix, and we apply this tensile test, and we have the nucleation of void, the growth of void, and finally the coalescence of void. So here's some image coming from our other colleagues in charge to do the experimental observation. So briefly, this work is based on the collaboration on the national project in order to understand the evolution of damage during the processes. So here is this initial state of a billet coming from casting processes in which we have a nodule. And this nodule is very difficult to simulate, so we have to put a mesh on this in order to have the simulation of this nodule. So you can see here that during a tensile test we can have a debonding between the nodule and the matrix, and we create a localization of equivalent stress in this zone. Okay, few slides. Okay. So I finished with this application. It's strange because we start with level set with this thematic of heat transfer. I finished today with this, but it is very interesting because the heat transfer, heating and quenching, is also multi-physics and multi-scale problem. So it's not very easy to deal. We start for heat transfer only from the solid side, but we need to have the surrounding in order to understand the heat transfer. So here is the very big oven here. Here a smaller one, and we simulate this using this level set interface, in which we have only one mesh. So for all the building here, and we have a moving object. It's a solid object here, meshed also with the frontier describing by the interface. So here is just an example of natural convection of a disk. So it's a very simple test, natural convection, but in fact it's not so easy to compute. We have to perform too. So here is the evolution of temperature in 2D, and here is in 3D with the corresponding meshes. So the line here, we have 3 thermocouple in the part here. So the continuous line, the experimental observation, and the dot line is for the numerical simulation with different approach of our numerical platform. So I escape this one. And just to finish, because I promised to my colleagues to show this. So here is the the use of this one to have a very fine description of the boundary of complicated bodies. So we use the Immersed Volume Method, Anisotropic machine, but it needs also a high computer machine and parallel adaptation. And here is also the same, but at other boundary. Okay, just to finish, so concluding remarks. So our core business is material forming simulation. So for us, it's important to know the origin of the material until the end of the part, all the mechanical properties, including forming with the microstructure evolution. This is very important. Heat treatment, including heating, induction, heating, and quenching, but also damage prediction for the in-use properties. So we use only finite element approach, but we try to improve this finite element approach for fluid structure interaction using the immersed domain approach and the level set. For us, it's very easy to represent moving object, and it's also very interesting for multiscale and multiphysics approach. The drawback is it's a very large computational time, and also space location, space. So the effort is on this one in order to give a good answer to the industrial requirements. Thank you very much for your attention.